In this lecture, we're going to continue talking about combined loading. We're going to do some slightly more sophisticated examples than what we were able to do in the last lecture. So in this example, here I'm using SI units this time. We have a round bar that's fixed on one end, and it has an arm that's hanging out. And on that arm are a couple of loads, 10 kilonewton down and 25 kilonewtons out. And we want to find the state of stress at 3 points on this bar: A on the top, B on the side, and C on the bottom. Now, we talked about how last time we wanted to approach these problems was to make a free body cut at their point of interest and then see how each of the reactions contribute to the stress state at those points. Well, if we want, we can do one step before we do that. You can call this step 0 if you want. And that would be to simplify the statics. So although we could make a free body cut at point A and find the reactions directly, what I would suggest, if you have anything like an overhanging arm or the geometry looks a little bit complicated, is to simplify that first. And what we need to do is to resolve those forces to the centroid of the cross section of the bar that we're looking at. So in this particular problem, let me redraw the bar that we've got. I think I can do a little bit better job than that. Let me try that again. We have this 25 kilonewton load at 0.3 meters from the centroid. So this is trying to show that this is located at the centroid. So we're going to replace that force with an equivalent force and moment. Now the force will be in the axial direction now at the centroid, and it's still 25 kilonewtons. But we're going to also have a bending moment that goes on the front of this bar, kind of from left to right, around that direction. And that bending moment, I'll call that M1, is going to be 25 kilonewtons times 0.3 meters. Now we have to deal with a 10 kilonewton force. It will also come over as a force and a moment. Anytime you move a force, it moves as a force and a moment. In this case, it moves as a torque, which is a special kind of moment, if you want to think of it that way. And the torque in the front will come around this way. So I will call that torque T. See, it's pulling down this way. It's going to cause a torque that goes that way. And that torque T will be 10 kilonewtons times the 0.3 meters. So then that first step is always to simplify the problem. And now this looks a lot like the other kinds of problems that we've worked in the past. All right, let's now take a cut at our points of interest, which are 1.5 millimeters from the free, 1.5 meters from the free end. We have an axial force going out of 25 kilonewtons. We have an axial force that goes this way, 25 kilonewtons. Keep that at equilibrium. We have a torque that comes around this way in the front. I'll call that T. We know the value of it. So we have to have an equal and opposite torque, T, on the backside. We have a bending moment that goes left to right. That's my M1. We have to have an equal and opposite bending moment that goes that way. That's my M1. We have a 10 kilonewton force that comes down. We have to have a 10 kilonewton force that goes up. And in addition to that 10 kilonewtons, as we move further and further down to get to 1.5 meters, we're also going to have another bending moment that puts the top in tension and the bottom in compression. So it's going to go top to bottom, and I'll call that M2. Now sometimes these things can be kind of hard to draw and visualize. It takes a little practice sometimes, and be careful as you look at my picture. It might be a little bit confusing too, but try to see where these moments are coming from. So that M2 would be 10 kilonewtons times the 1.5 meters. Alright, so we have 3 points. Let's just do them all at once. Here's the top view of A, here's the side view of B, and here would be looking through the section like a top view of C. Alright, so we're going to go through each of these reactions and see how they cause stress at those particular points. Alright, so let's do the easy one first, 25 kilonewtons. It's going to cause axial stress for each of these problems. And in each of these problems, it's going to be the force divided by the area of the cross section. And let's see, I said it's a 40 millimeter diameter. Let's convert that into meters. Okay. So now we're done with that one. The next thing we see is that we have a torque. Now on the front side of the bar, this torque goes around in this fashion. That would be a clockwise fashion. So that causes shearing stress on each of these points that go around in that direction. The shearing stress at C will point this way. At point B, it'll point up. And at point A, it'll go opposite to the direction of C. So if we're looking down at the top, at point A, the shearing stress will go this way. If we're looking at point B, the shearing stress is pointed up on the side view. And as we look down at C from the top, it'll go this way. Once we have one of those arrows, we can pencil the rest in for equilibrium. Just in those directions. Now the value of the shearing stress is given by the torque times the diameter over 2 divided by the polar moment of inertia. It's a little cramped. Tell you what, let me move some of these over a little bit. There we go. Alright, so this will be the torque, which we said was 10 times 0.3 kilonewton meters, so that would be 3 kilonewton meters, times the diameter over 2, that would be 20 times 10 to the minus 3 meters, divided by the polar moment of inertia, which is pi over 32, the diameter to the 4th power. So we're going to have that exact same term for each of these 3 shearing stresses so far. And that should have been to the 4th power on the first term. Alright, so now we're done with the torque. Let's take a look at the moments next. We have a moment M1 that puts the near side in compression, and it puts the far side in tension. If we look at this on a side view, on an end view of this cross section, here's A, B, and C. It's bending about a line that goes through the centroid like this. So it puts point B in compression, but it does not affect A and C. So since it puts it in compression, I'm going to subtract off from the P over A stress. So I'm going to have a minus M1 times Y over I. All right. So we're done with M1. Now let's take a look at M2. M2 puts the top in tension and the bottom in compression. Point A is in tension in the axial direction, so we're going to add to this the moment value, which is M2. It's 10 times 1.5 kilonewton meters times the radius of the bar, 20 times 10 to the minus 3 meters, divided by the bending moment of inertia, pi over 64, diameter to the 4th power. Now at point C has the exact same stress, except it's in compression from the bending moment. So now at point C, we're going to subtract away that axial stress term. 10 times 1.5 kilonewton meters. It's going to be 20 times 10 to the minus 3 for the radius of the diameter over 2, divided by the bending moment of inertia, pi over 64, diameter to the 4th power. So that takes care of M2. And the last thing that we want to look at then is the transverse shearing force. It goes down in the front. Let's draw another cross section. The formula for that is VQ over IT. Where Q is the first moment of area that we're going to shade in from the point of interest to either the top or the bottom of the cross section. And at point A we have no Q area, and at point C we have no Q area. So we don't get any shearing stress at points A or C from the 10 kilonewton force. We will get some shearing stress at B. The area that we shade in will be the top half. That shearing stress goes down on the right side of point B, so I'm going to subtract off, and I'm going to write this here as VQ over IT, and let's go over here to fill that in with the numbers. The V is 10 kilonewtons. The Q is Y bar A. Y bar for a semicircle is something that I will give to you, but it's 4R over 3 pi. The area of a semicircle is a half pi r squared divided by I, pi over 64, diameter of the 4th power, and the thickness of the cross-section point of interest would be the diameter, and so that would be another 40 times 10 to the minus 3 meters. So that would go in here for this value. I want you to notice a couple things. Notice how the shearing stress at point B, those two terms work against each other. That's why they're subtracted. In one case, the torque is causing the shearing stress to go up as we look at the side view. In the other case, the transverse shearing force is causing the shearing stress to go down as we look at the side view. So they work against each other, so we have to subtract them. Without calculating the numbers, I don't know which one's going to win. It's probably the torque. But the final outcome of that subtraction will tell you which direction the arrow really points on that block, as it is shown, or if it points in the opposite direction, the VQ over IT happens to be big enough. Now, another thing I want to point out about these problems is it's not very easy for me to give a point that is not at the top, side, or bottom of the cross section in these type of problems. Now, if we do have two planes of bending, I could ask you which point has the most bending stress on it, and that way, and what you would do is you'd have to find the resultant bending moment, and based on the relative values of the two bending moments, then you can calculate the maximum bending moment. So let's talk about that. Let's get a new page. So let's look at this example. We have our round bar again, and we have two bending moments, top to bottom and left to right, 10 and 20 kilonewton meters. Suppose I wanted to find out what spot on the cross section had the maximum bending stress on it. What I'm going to do is I'm going to represent both of these bending moments with double-headed arrows. So the 20 kilonewton meter bending moment bends left to right. That's like if I look at the cross section, that would be represented by a double-headed arrow that goes up and down. The other one, 10 kilonewton meters, it bends top to bottom. Using the right-hand rule, I can figure out which direction that double-headed arrow points. That would be a double-headed arrow that would point to the right. Now, if I wanted the resultant moment, that would be the square root of the sum of the squares. Let's see what we get for that. That'd be 22.4 kilonewton meters. If we wanted to find out where on the cross section had the most tension or compression, we can construct a vector diagram. Where this is 10 kilonewton meters here. Let's move it over here just a little bit. And we can call this angle theta. So the tangent of theta would be equal to 20 over 10. Let's see what that would be. (63.4 degrees). So on the cross section, at an angle of 63.4 degrees would be either my maximum tension or my maximum compression, and 180 degrees from that would be the opposite, maximum compression or maximum tension. Now we can figure out which one is which by looking at these diagrams. So let's see. Something looks a little bit off to me on this one, because I would suspect that the maximum compression should be down here somewhere. Well, this will be the resultant of the force, so that's true. So the resultant moment would go this way, and if we use our right-hand rule, the maximum compression would be here, and then over here would be the maximum tension. Okay. So the math is right. It's just you have to be careful about how you interpret that double-headed arrow. All right, so then if we wanted to find the stress here, that would be equal to m, the resultant moment, times y, the diameter over 2, divided by the moment of inertia, pi over 64, diameter to the 4th power. Alright, so let's do another example. Here's a cantilevered pressure vessel. It's got a force on the end of it. We'll do our same things that we need to do. We're going to cut this at our point of interest. Draw our free body diagram. And if we have 25 kilonewtons coming down, we have to have 25 kilonewtons coming up. And we're going to have a bending moment that's going to be equal to 25 kilonewtons times 2 meters. Our point A is on the side of our bar right here. And we want to see how these reactions contribute to the stress at point A. First of all, we'll have our pressure vessel stresses. The axial stress is the smaller of the two pressure vessel stresses. It's equal to the internal pressure times the inside radius divided by 2 times the wall thickness. Now let's see. The total difference would be 4 millimeters, so the wall thickness would be 2 millimeters. And the hoop stress goes around the circumference. That would be the larger of the two, is PR over T. Again, we need to use the inside radius and then the thickness be 2 times 10 to the minus 3 millimeters again. We're going to have a bending moment. It puts the top in tension and the bottom in compression. It does not affect point A. So we're done with that one. We will have a transverse shearing stress. Let's draw the cross section over here. Here's my point A. What I'm going to do is I'm going to shade in from my point of interest to the top of the cross section. And here we have this thin ring. What we need to do is we need to find Q for that thin ring. We're going to apply the formula tau is equal to VQ over IT. That shearing stress will go down on the right side because the force goes down on the right side. These other arrows get penciled in for equilibrium. Let's call this one sigma x. We'll call this one sigma y. And the shearing stress tau xy will be equal to the VQ over IT term. Let's fill in some of these terms. So V is going to be 25 kilonewtons. We'll talk about Q in a moment. I is going to be pi over 64 outside diameter to the 4th power minus the inside diameter to the 4th power divided by the thickness of the cross section. Now, the thickness of the cross section is going to be this dimension plus this dimension. The thickness, the T in VQ over IT, is a different T than in the pressure vessel T. It's the total thickness of the cross section. So this is going to be 4 times 10 to the minus 3, okay, because it's 4 millimeters thick for the total cross section. Now the Q, here's how I would like you to think about doing the Q. What we're going to do to calculate the Q for a ring like this is we're going to take Q for a solid bigger semicircle and we're going to subtract away Q for the hollow part. That's going to leave us with Q for that ring. So let's write it down here. For a larger solid semicircle, it's going to be 4r over 3 pi times the area, a half, pi r squared. And now we're going to subtract 4 r over 3 pi times a half pi r squared. So when you calculate this term out, you can put it in there for Q. Now, you should expect to see a combined loading problem on your third test, where it's kind of a straightforward combined loading problem. On your final exam, you should expect to see a combined loading problem where I will ask you some additional things, such as, now that we've calculated these stress components, what are the principal stresses? Let's make a new page. So I'm leaving this as symbols, but suppose we've calculated sigma x, sigma y, and tau xy for our problem. If we want to find the principal stresses, we can use more circle. We can go through our whole process where we plot sigma and positive tau. We got maybe our sigma x and our tau xy point right here. That'd be our x point. Maybe this point is our y point, which would be sigma y comma minus tau xy. We draw our circle. We find our radius. And sigma p1 and 2 would be equal to the average plus and minus the radius. Now, in the previous problem, we had a pressure vessel which created what's called a biaxial state of stress on the surface of our component. On the outside surface of the pressure vessel, the third principal stress would be equal to 0. On the inside of the pressure vessel, the third principal stress would be equal to the value of the pressure, but the negative of that number. Now, on the outside of the pressure vessel, then the third principal stress would be 0. So this would be a case where we have an out-of-plane absolute maximum shearing stress. So I may ask you to find principal stresses. I may ask you to find the absolute maximum shearing stress. Another thing I can ask you to do is apply a failure criterion on your final exam. We'll talk about that in a couple lectures. I can ask you to find the strains for this particular stress state. Okay, and just as a reminder, in order to find the strains, we would use Hooke's law, 3D Hooke's law. So epsilon x would be sigma x over E minus nu, sigma y over E minus nu, sigma z over E. Epsilon y would be sigma y over E minus nu, sigma x over E minus nu, sigma z over E, and so forth. The shearing strains, gamma xy would be equal to tau xy divided by the shear modulus G. And if we had them, let's just go ahead and write these down. Gamma xz and gamma yz can be found by taking their respective shearing stresses and dividing by the shear modulus. So I can ask you to find stresses in the xy coordinate, strains in the xy coordinate system. I can ask you to find principal strains. So knowing that strain state, you can do a Mohr circle of strain. Alternatively, if you've already found the principal stresses, you can find the principal strains by plugging the principal stresses into 3D Hooke's law. Okay, so there's a lot of things that you can do with these combined loading type problems, and they're very good to put on a final exam because I can test you over a lot of things in one problem. Alright, so we'll make this lecture a little bit short. We might come back and fill in with some more examples later on.